A cell of internal resistance 2 ohms and electromotive force EMF 1.5 volts is connected to a resistor of resistance 3 ohms. What is the potential difference across the 3 ohms resistor? First, let me identify a couple of terms. A cell means a battery. Internal resistance is the resistance of this battery. EMF of 1.5 is the voltage labeled on the battery, and is asking which is voltage, and is asking for the potential difference across a resistor. Potential difference is also voltage, and the abbreviation is PD. So here we have two abbreviations. One is EMF, the other one is PD. EMF converts chemical energy from the battery to electrical energy, and PD use this electrical energy in other forms of energy like heat and light. In terms of a diagram, we can draw a circuit based on the information with the cell connect to its internal resistance and a dash box here to indicate that's the cell or battery, and that is the resistance connected to the terminal of this battery. This longer line means positive, and the shorter line is the negative side of the battery. One alternative and very quick way to do this when you have two resistors in series in a circuit and one battery providing energy to both is using the formula for potential divider. So potential divider is very simple. It's just like if you have a voltmeter with the terminals connected to the terminal of this resistor, and you want to read the voltage across this resistor. The formula for potential divider does not include current, which is a great advantage. So to do that, the formula is the voltage, output voltage, which means the voltage on this resistor, the output voltage here is on this, is equal to the input voltage, which is 1.5, times the resistor where you want to measure the output voltage, 3, over the sum of the resistors connecting series in the circuit. So in this case, it's 3 and 2. They are actually connecting series, so you'll be 5 ohms. So the answer for this question is 0.9 volts. So what happened is from the EMF, which is 1.5 volts, just 0.9 volts of this is going to be delivered on this resistor. The rest of the energy will be consumed with this internal resistance of this battery. Question 9. A 100 ohms resistor conducts a current with changing direction in magnitude as shown. So this is instead of have a sine wave, we have a square type of wave. There is a setting on the oscilloscope that we can press and select how we want the wave being presented. So in this case is our option to say square, so that's why you see a square shaped wave. So the question is asking, what is the mean power dissipated in the resistor? So the resistor values provided is 100 ohms, and from the graph you can obtain the value of the current, which oscillates from -1 to 2 amps. So this is the formula for power in terms of current and resistance. So when the current is the maximum value, which is 2, the power based on this formula is 400 watts. For the minimum value of the current, the power, now here, even though if you want to use a negative sign, when you square, it's positive anyway. So the power is a positive power of 100 watts. So the mean power is the average of the maximum and minimum value of the current. So 400 plus 100 divided by 2, 250. And this is the answer. Now, this is a very simple question when actually you know this formula and you know how to use the mean power in terms of the average of values. And as you notice, we have as options for answer 400, we have 100, and this one here is kind of extra. So you can be a little bit deceived by the answers and mark the wrong one. So just pay attention on this one. It's a simple question, but you need to know a couple of details in order to get the right answer. Question 10. Two wires, P and Q, made of the same material and the same length, are connected in parallel to the same voltage supply. So a lot of things here are the same. Wire P has diameter 2 millimeter and wire Q has a diameter of 1 millimeter. What is the ratio between the current in P and the current in Q? Here is a simple diagram that represents the problem. So we have a P wire with diameter greater than a Q wire, and both are connected in parallel, which means that if the voltage on those terminals are exactly the same. So also the problem provides a couple of more things. One is they are made of the same material, which means they have the same resistivity and they have the same length. So now what they are asking is the ratio between the current in P and with the current in Q. To find this ratio, we are going to use Ohm's law formula because the ratio is asking for the current, and we have here the voltage is the same, and we have the elements to determine a non-numerical value for each resistance. So this is the voltage for P, RP, IP, and this is the voltage for Q, RQ, IQ. Since the voltage on both wires are the same, we can equal those two equations. So RP, IP is equal RQ, IQ. So I want to isolate the current to look like this. So I will keep IP here, move IQ down here, and RQ, I will keep it this way, and I move this one down. Now I'm using two new sets of formulas. One is for resistance, by definition, resistivity times the length over cross-sectional area, and a cross-sectional area of a circle, because this is a cylinder shape, is pi over 4 d squared, diameter square. So making my substitution here is rho L of A over A, and here is rho L over A, but all this here is related to Q, all this is related to P. Now, because both wires have the same resistivity and length, so we can cancel here. So resistivity and length can go. Okay, so after I eliminate all this is what is left in this ratio. So I'm kind of moving my result right here. So this is on the numerator, so I will keep just like it is, and I will flip this denominator, AP. Now I'm going to use this and make the substitution. 1 over pi over 4 d for q square times this one is pi over 4 dp square. Now we can eliminate this with this. So now this is what is left, and the problem provides the value of the diameter for each wire. The diameter of the wire P is 2 millimeter, and the diameter of the wire Q is 1 millimeter. So I square both, so I need to square the units as well. So this is 4 over 1. So now we can cancel those units, and the ratio between current on P over current on Q is 4. Okay, so that's the answer, 4. So beautiful problem. Just make sure that you understand because they are in parallel, the voltage is the same. So you can find the relationship between the currents through Ohm's law. And then you can replace the values of the resistance formula and remember the area. And the rest is pure algebra, basic algebra. I did with very detailed steps, so you know exactly what I did to get this answer. Next, problem 11. What is the total resistance between points P and Q in this network of resistors? We can notice here that those 3 resistors, they are in series, and these 3 resistors, they are in series. So I circle here those 3 resistors in series, and I'm going to find this value. So because they're in series, so the partial resistance here on these branches, this one, you have to add them. So there will be 16 plus 16, right? 8 plus 8, 16 plus 16, 32. So this is 32 ohms, and this is the same thing, 32 ohms. Now, one really cool thing that you can do when you have resistors in parallel, because now we have 32 in parallel with 16, in parallel with 32. So you have those 32 parallel with 32, so they are equal. So you can find the equivalent resistor of both by dividing by 2. So I kind of rearrange this circuit, this network here to this, because it's the same thing. You have P and Q, those are the terminals. So we have on the top here 32, at the bottom we have 32, but because they are in parallel, you can kind of switch position. You not change the voltage or the current that is flowing across each resistor. Okay, so now I'm going to reduce this circuit to just 2 resistors. So to do that, I need to find the equivalent between those 32. So you can do even mentally. You can, because they are in parallel, they have the same value, you'll be 32 divided by 2, which is the amount of resistors here. So that will be 16. And then you have the other one, which is 16 down here that we didn't touch it. So our last step is, now we have those 2 in parallel, they are the same value. So you just get one value divided by 2 because you have 2, right? So 16 divided by 2 is 8. So the final answer for this option is 8 ohms. So this is the sequence that I follow to find the answer for this problem. An alternative is also stop right here on step 2 and add the inverse of the resistors. 32 inverse plus, I'm right here on this step, 32 inverse plus 16 inverse equal inverse. And from here, you could obtain the answer without going through these steps. Problem number 12. The diagram shows a low voltage circuit for heating the water in a fish tank. So this is the fish tank. This is the heater element connected to the power supply. The heater has a resistance of 3 ohms. The power supply has an EMF of 12 volts and an internal resistance of 1 ohms. At which rate is energy supplied to the heater? First, to understand what this problem is asking, you have to look here at the question. At which rate is energy supplied to the heater? So the answers are all in watts. So of course, this is a electrical power problem. But where this come from? So remember that power is the rate of energy. When you say the rate of energy, actually is saying the energy used, supplied, dissipated over time. So this word rate means over time, something over time. So this something in this case is energy. So energy over time is power. So that's what we need to find, the power of this heater. So this is a circuit diagram that represents this picture or this drawing. One information provided here is low voltage circuit, which means a battery. So this is the battery with EMF of 12 volts. The internal resistance of this battery is 1 ohm. And the heater has a resistance of 3 ohms. So here are the formulas for power in terms of current, resistance, and voltage. So each one we can use to calculate this power supply to the heater. Using the process of elimination, what we have here, we need to find the power on this resistor. So we have the value of the resistance. So we are going to select one of these options, this or this. From these two options, each one is going to give me the answer quicker. If I use this one, I need to calculate the current flow in the circuit. If I use this one, I just need to find the output voltage on this resistor. So for my selection here, I'm going to work with this one because I can use the potential divider formula to find the voltage really quick in the circuit. So the potential divider, which means if I place a voltmeter right here, what will be the voltage on this across this resistor? So that will be my V out is equal my V in, which is 12, times the value of the resistor that I need to find the voltage, divided by the sum of the resistors connecting series in the circuit. So it will be 3 plus 1, 4. So 12 divided by 4 is 3. 3 times 3, 9. 9 volts. Perfect. Now I have my voltage across this resistor. The resistor is 3 ohms. So I just use this formula, V squared over R. And this is my power, or the rate of energy supplied by the heater. So 27. Before I leave this problem, I just want to make a couple of observations. One is a great example that you can differentiate EMF with PD. So the EMF is 12 volts and the PD will be this voltage right here, which is 9 volts. So the PD is going to transform the electrical energy provided by this battery into a thermal energy by the heater. So that's the difference between EMF and PD. So both are related to energy, but is how they transform one energy to another that make the difference. Question 13. Which symbol represents a component whose resistance is designed to change with temperature? First, when you see a box like this, that represents a resistor. So a rectangle is used to represent a fixed value resistor. So when you have other lines or arrows on that resistor, means that will change with, depends on some situation, will change its value. So it's a variable resistor. So the first one is a variable resistor. So this is a kind of slider that can set to a low or a high value for this resistor. So the next one is a thermistor. Is a type of resistor that change its value with the temperature. So when it's cold, this thermistor will have a high resistance. And when it's hot, this thermistor will have a low resistance. The last symbol represents a light-dependent resistor, or LDR, is a resistor that changes its value based on the amount of light. So we'll have a high. The last symbol represents the light-dependent resistor, or LDR. So it's the type of resistor that will change its value based on the amount of light. So if it's dark, we'll have a high resistance. And if the environment is bright, we'll have a low resistance. So for this option, to answer this question, which one is designed to change with temperature, is the thermistor.